Nucleophilic substitution, the last of the mechanisms, all right? It exhibits duality of mechanism. The same guy, the same exact reaction can go two different ways, all right? That's the weird part about this, all right? You can actually have, I could take a halogenated alkane, add water to it in the right catalyst, and get the same product, but depending on what alkane I used, it can go two possible ways, all right? And the first one is called Sn2. Now, I told you a minute ago that that's weird because the 2 does not refer to how many steps you have. This is only a one-step mechanism. The 2 refers to what order it is, all right, second order. Now, you're going to learn about kinetics in probably January or February. And basically, what kinetics has to do with is how many guys, how many atoms or molecules are involved in the slow step. How many things are actually involved in the rate determining step. Remember the cookie example, okay? If I have chocolate chips, how fast I mix those chocolate chips in makes no difference if the baking takes 15 minutes. I'm going to be waiting around, all right? So let's talk about this first mechanism. And the picture is all there, but I wouldn't normally have done this. Last year, or not last year, yeah, probably last year even, I would have had you draw this in because I want you to view this almost like a video, like of what's happening here. I actually have a video clip of it. I don't know if it's coming up next or not, but yeah, it is. So I'm going to rewind this in a second. Okay, turn that light off and show this again. This is the one-step mechanism. It's very simple. This is exactly what happens. You might think to yourself, well, this is going to be the easiest one. That free radical halogenation had like 6 steps plus other things that could have happened. Yesterday's electrophilic addition had 2 steps. This guy's only got 1, and it all happens at once. Here's what happens. You watch it. God bless you. All right. There's your OH. There's your alkane with the halogen on it. The halogen is the green. The OH, that's red and white. Okay. Let's see. The alkane would be methane in this case. Okay. Let's watch it again. That's all that happens. As this guy attaches, that guy leaves. But you notice the whole molecule inverted. Did you see that? Watch it again. Well, one last time. Watch what happens to the actual methane molecule. See it? Yeah. It's completely backwards from where it was. This guy adds to the opposite side.
Can you play one more time?
No. This guy adds to the opposite side of where that green thing was. All right, that green thing's your halogen. All right, bromine, chlorine, whatever. The OH is over here. So as this guy's adding, that guy's leaving. All right? We call him a leaving group, actually. We're going to see why later. All right, turn the light back on. All right. Now, let me break that down for you, step by step, what's going on here. Actually, it's only one step, but again, thinking of it as like that video just showed it to you. At first, you've got your OH, and you've got your methyl groups or whatever around of carbon that's going to be attacked here. And we call it attacked by this. What do you think that guy is? If he's being attracted, if he's negative and he's being attracted to this carbon, what do you think that charge on the carbon is? Well, let's take a look. Bromine is more electronegative than carbon. And so he's going to pull the electrons that way, right? Which makes the carbon slightly positive. It's not a carbonium ion. Don't get that confused. A carbonium ion is when he loses something and it ends up having a total positive charge. He's an ion. No, he's got a slight positive charge there because the bromine pulled the electrons a little closer to him. And so this negative OH, which you've got around here from the water molecule, is going to be attracted to that carbon there. I think that's what the first thing's going to tell you there. No, I'm going to show you the whole thing first. All right, so I'm going to explain it all, and then the notes will come up here, and you can put them down in a second. All right, so that's the first thing that happens. This guy's attracted there because he's slightly negative, and over here he's very negative, and he's slightly positive there. Then what happens? As this bond forms, that bond breaks. Okay, so the next step, and you have all 3 of these steps down there. It's actually one step. It's all happening at once. Look what happens to this guy. You know what these drawings mean now. He was a tetrahedron, right? Yeah. Only he's kind of facing this way. And this guy's in the plane, this guy's in the plane, that guy's coming out, that guy's going in. Look at this. That's all in the same plane. Okay? It flattens out. See it? As this guy forms, it's going to push those guys away because this guy's breaking. So at this point, here's what's happening. This bond is being broken, and this bond is being formed. All right? And then finally, what happens, as the OH finally attaches and the bromine leaves, you've got your bromide ion, all right, that was formed eventually. All right? So that all happens in one step. Now, the thing is, the crazy part about this is, different things about the molecules will determine whether this guy goes by SN2 or SN1. Some of the things you got to worry about as we're talking about these. How many carbons are going to be around this guy? That's going to be a factor. What's the bromine or the halogen that's attached? Is it fluorine, bromine, chlorine, iodine? That will be a factor. All right, those are the two biggies we're going to watch for. Okay, let's write these notes down. I've explained it, but now these are for your notes. It's a nucleophilic attack of an OH ion, hydroxide ion, onto the backside of an electrophilic carbon, away from the bromine, that is. Write all that down, and I'll explain it again. So you have it written down and you understand it. I think the dashes are correct today. They're a little off yesterday.
Is there one nucleophilic or two?
Probably two. I just misspelled it there. Thanks for pointing that out. You know, I'm going to ask you the kind of questions you already saw me ask you in the worksheet you just did. Who's the electrophile? Who's the nucleophile? Who's the carbonium ion, right? Well, in this case, if I showed you this mechanism on the worksheet or on the test, and I asked you to identify the nucleophile, what would you say? Who's the nucleophile in this case? You have to think. The nucleophile is attracted to nucleuses. Nucleuses have a positive charge. The OH. Exactly. See how, again, I've been trying to teach you like that for the past 2 years, in some cases 3 years for some of you. Not in this class, though. I've been trying to teach you guys like that for a long time. You can't just memorize your way through. Oh, say OH is always a... No, it's not like that. You got to think about it. All right? Now, the electrophilic carbon, what does that mean? Well, it's electrophilic carbon because there's other carbons on there. The one that's going to be electrophilic is going to be the guy who is attached to the halogen because he had some electrons pulled closer to the other guy. So he's going to be slightly positive there. If he's slightly positive, it's going to be electrophilic. All right? Now, does that make him a carbonium ion? At no point do you have him, but you will in SN1. That's the crazy part about this. All right, let's see what else it says here. All right, this results, as you saw, as I explained, in complete stereochemical inversion. If you had an R, you're going to now have an S. By the way, in this case, you have two H's, so you're not going to have a actual stereochemical molecule. You don't have a chiral carbon. But if you did, you would basically end up with complete stereochemical inversion because you now have added the OH onto the opposite side of where the bromine was. So it's attacking from the back side of where the bromine is. That makes complete sense. There's a slight negative charge on this bromine, and there's a very negative charge on the OH. They're not going to be on the same side. They're going to be attacked to the opposite side, the back side. Okay? All right. Finally, actually, I don't know, maybe one more thing after this. How many dashes do I have there? Okay. So what determines how well this reaction goes, how fast this reaction goes? Well, the main thing for this guy is something called steric hindrance, which is basically the interference of adjacent alkyl groups. Normally, we're used to saying for our carbonium ions, we want more carbons around them, right? That stabilizes the charge, correct? In this case, it's the exact opposite. If you remember my animation, which I showed like 500 times, and you watch it again, if you were to watch it again, it purposely used methane. Okay, there are no other carbons around that carbon, so there's not a whole lot of stuff in the way. I want you to realize this, guys. Watch. The big factor in this case, this guy's got to get in there. Now you got to remember to do that, to get in there. These carbons, these CH3s, are not just CH3s. They're not just like a CH3. It's a C with an H, an H, and an H. So they're going to be in the way. If I have another CH3 here with an H, an H, and an H, it's going to be blocking that attack, the path for him to get in there. It's going to be harder for him to get in there. So the more crap around that carbon, the harder it is for that OH to get in there. Okay, that's a big factor. Okay, there is one other factor though that would determine this too. We're going to talk about that when we get to the next one. So anyway, you would expect this guy to be the opposite of electrophilic addition, where your best bet was tertiary, right, where you're stabilizing that carbonium ion. Here, your best reaction is going to happen, your fastest reaction, and the more likely reaction for an SN2 is going to be a primary carbon. And when I say primary, I mean the bromine's on the primary carbon, you see? Or chlorine or fluorine. It doesn't have to be bromine. All right, secondary and tertiary, all right, will be last because there's more crap around it to get through. Got it? All right. Now, here is the Sn1 mechanism, which is a two-step mechanism. Write that down. Or do I already have it written down?
Yes.
Okay. Now, again, I've got this guy broken down. You only have the. I redid it. I said this year. I did it to try to save on paper and everything, and to make it as easy as possible. But I'm going to look at it stepwise, like I always do. Okay. Look at this guy. This guy's got R groups all around him, so it's going to be tough, assuming they're all carbons and with hydrogens, and maybe even ethyl or propyl or butyl groups around him. It's got all this junk here. It's going to be hard for an OH to get in there. Okay. However, because he's got all those guys around there, that bromine, if he leaves, it's not that big of a deal. If he just leaves, and he does, like this, and forms a carbonium ion, and that's what he does, you actually can stabilize that pretty well because it's got all these R groups around it. So, well, why would he want to leave? Well, he could be pulled off for different reasons. A solvent makes a difference too. How strong the attraction is here. I would expect guys like iodine and bromine, for example, to leave pretty easily. Look at iodine and bromine on a periodic table. Look where they are. They're not that electronegative. If I had fluorine on there, would I expect him to leave that easily? Probably not. So this guy's going to have a couple of factors involved with him. Number one, all right, what kind of a leaving group do I have here? Do I have a guy who's attached really strongly, like fluorine? Probably not going to want to go this way as much. Number two, how many R groups do I have around here? The more methyls and propyls and butyls I have around there, around this central carbon, the better chance of him being stabilized by the carbonium ion. Now, notice what happens in the next step. Again, all these are going to come up in a minute. Notice what happens in the next step. Or maybe I got to double check that I don't have the whole thing. Yeah, no, okay, so there. The first step, this first step, of course, is not going to happen very easily. Even with bromine, even with a lot of carbons around it, it's going to be the slow step. And it alone is going to determine the overall rate of the reaction, unlike last one, we're going to go back to in a little bit. This first step is very slow because the bromine, he was attached. He was happily attached. All right? And when he breaks off, he forms an ion. Ions are not happy. They're going to try to gobble somebody up real quickly to get back to being neutral. All right? So this is a slow step. I may have to heat him up to get him to do this, right? I may have to give him some energy to get him to do this. I may have to find a solvent where I can stabilize the guy better. I might have to make sure I've got lots of R groups around him to make sure he's going to be happy enough to do it. But eventually I can coax him out of there and get rid of that bromine, make a bromide ion on that. But that's the slow step. Let's go back to the other one a minute, if we just saw. In this case, it all happened at once. So the water, OH, and the alkane, the halogenated alkane, haloalkane, they're both involved in the only step. In this case, who's the only guy involved here?
Bromine.
Well, this compound, right? We're going to add OH to it. But the amount of water I use means nothing, or alcohol, or whatever I'm using for my OH source. The amount of OH I use means nothing to this. Because once I form this guy, the OH is going to snap him right up, right? It's this step, this first step, which is totally based on him and him alone. So, you know what? This is the weird part about this. This is why it's called the Sn1 mechanism. His entire rate is dependent only on the concentration of him. As long as there's any OH around, all that matters is how much I have of him. How fast it will go depends on him. Him and him alone. Okay? That seems weird, but if you think about the cookie example again, it makes sense. It makes no difference how fast I add chocolate chips or how fast I add the flour or the sugar. It only matters how long it takes me to cook that, bake them. It takes me 15 minutes to bake it. I mean, I could mix those things up in 2 minutes, 3 minutes, 5 minutes, 6 minutes. It doesn't make any difference how fast I do that. I'm still waiting. This is the slow step. As soon as that's made, guess what happens? An OH is going to gobble him right up, going to attach himself right on there really, really quickly. Okay, so the rate depends on the stability of the carbocation. And in this case, what would you expect? Like I said, the tertiary is going to be the best. It's going to be the exact opposite of what you just saw for the SN2. Tertiary is the best, then secondary, and then primary. I told you this is the most, this gets confusing. This is the, thank God it's the last one, but this is exactly what I meant by this. You're seeing, yeah.
Is it supposed to be carbocation?
Carbocation or carbonium ion, either way. I told you I've used both terms already. What's wrong with it? Oh, it would not. Yeah, carbocation.
Okay,
I mean, I don't need the other ions.
Why do you have
I don't have to have the other ion.
3/2/1?
That's not 3/2/1. That's tertiary, secondary, primary. Like I said. That's what it means. We have a tertiary. I didn't put the degree sign above it, but that's tertiary, secondary, and primary. We've seen that before, right? You can put the little degree sign. All right? Yeah.
What do you say carbocation?
It is an amazing thing. If one person asks a legitimate question, then the next question gets less legitimate, and then we're going to hear Austin now. What do you think, Austin? What's your question going to get?
It looks like carbocation.
Exactly. The least legitimate question now comes up.
Always think that too, like,
I have,
carbocation.
you realize I've already, the first time I gave you the word cation was in Chem 1. We learned about it in periodic table.
Yeah.
Yeah, psychology. And you like to know.
Well, they should pick up on this one up here.
At that time, I said it's not pronounced cation. And I can actually prove this one because I actually recorded them this year. And so you can see me.
Well, you might have said it this year. It doesn't mean
I can also point it out in your notes from last year.
Okay, I'll bring
Okay.
a reminder.
I'll bet you any amount of money you want to bet. I will give, here's the options. You really want to make a bet?
Yeah.
You really want to make a bet? I will make this bet with you. You can find the word cation in your notes, and I can show it to you on me saying cation and pronouncing it this year like I do every single year.
I know he said it last year.
Exactly, I did.
You said you.
Or what's the second?
All right, so you can have a party the last day before Christmas if I'm wrong. But if I'm right,
Oh, that's not good.
what am I going to get? That's the question.
No, I
You're
don't
gonna get a
wanna
party
make
right
this
before
bet.
Christmas.
No. If I'm right, I gotta figure something out. Hey, you're not going to bet because I know I'm right anyway. All right, look at it.
Okay, so it doesn't matter if we talk now because it's really hard to just not say it.
All right, look at it. We're almost done. We're not quite done. Do we have any more dashes underneath that?
3 more.
Yeah, all right. Okay, yeah, because I haven't even finished the rest of this. Okay, look, I've made my carbonium ion. Okay? I've made my carbocation
Carbocation.
and carbocation, yeah. What's going to happen next is obvious. The second step is going to be this guy getting attacked by the OH. That will happen very quickly, okay? All right. The rate also depends on the strength of the leaving group, like I said a minute ago. Bromine is the leaving group in this case. The weaker the electronegativity, the weaker that bond, the better the leaving group. So you would expect iodine to be the best and fluorine to be the worst leaving group. They're called leaving groups. It sounds weird, but that's what they do. They leave. All right, so there are a lot of factors that determine whether this guy's going to go by SN1 or SN2. What time is this over?
19.
Okay, good, we have time, because I have quite a bit to tell you yet. At the end, I want to go over the kind of questions I'm going to get. You're going to see them in the worksheet probably, well, definitely tomorrow, because you guys have a double. If you're right and we have a double tomorrow, then you'll definitely see it tomorrow.
We're definitely right.
What happened? All right, so there's a lot of factors. There are a lot of factors involved here. How many R groups are around him? Okay, what's the leaving group? And there are other things that come into play, but they will determine whether this guy goes by SN1 or SN2. Okay, and so the same exact reaction. When I say the same exact reaction, I don't really mean exact. I mean, like I said a little while ago, if I have RX plus H2O, or I think I use NaOH, actually, NaOH. That's our source of OH. Yields ROH plus NaX. That was a reaction we did. All right, that was the reaction we did. If you, by the way, you may not remember. Yes, you will remember this because you actually like did a little wow moment. Remember I had the little stir up here, and I put a couple of drops of not food coloring, universal indicator,
Yeah.
and it changed color into a big flash of yellow. Remember that one? That was this reaction. I took a halogen. It was isopropyl. I forget which one it was, but it was something like that. It was like 2-bromo-propane and sodium hydroxide, and it reacted. Okay. Now I actually could have done that. I actually have the chemicals to do it with 2-chloropropane instead of 2-bromo-propane. And guess what happens if I use 2-chloropropane to that same reaction we did? It will, but it will do it much
Bigger.
slower. Much slower. And that's why I don't use it, because on that day, I'm just trying to, I'm trying to show you an example of this reaction. But if I were to do it, and I have done that, you end up waiting for like 5 minutes to see that flash. And the flash doesn't go like that, like a quick yellow, and then it goes to the next color. It's like very slowly, stays yellow for a while, and then it goes back. And it's much less dramatic, and it takes like 5 to 10 minutes to do it. Whereas the other one took only about a minute to do it, and it happens very quickly. Okay, but that's because chlorine's a worse leaving group than fluorine. All right, that's the reason.
When you say like the better leaving group, you mean like what leaves the
Right,
easiest?
this is the guy. Right, a leaving group is better if he leaves easier, and a guy who's going to leave more easily is going to be a guy who's not bound as strong, less electronegative, like iodine or bromine. Okay. All right, but my point, I had a point about writing this reaction down here. The crazy part about this is I'm going to get the same product, but it's not going to have been done the same way. There are going to be differences. Because if this R group is, for example, that, which mechanism do you think he's going to go by? Sn1 or Sn2?
Sn2.
Sn2. Because there's not a whole lot of junk around him, and I can't stabilize this guy as a carbonium ion like that. Okay? And especially if that X happens to be maybe a fluorine or something like that, right? Now, let's just say I've got this, where I've got methyl groups all around him, I've got an iodine on him, all right, and I do the same plus NaOH. So everything else is the same. He's going to go by a what? Sn1. Exactly. That's the kind of question I'm going to ask you. It's going to be the first question, I think, on the worksheet I'm going to give you on tomorrow. Okay, first kind of question on these types of problems. All right, which way is he going to go? All right, so let's finish this up. That's the last one for this, or is there one more underneath?
There's 2 more.
Well, no, but that's going to be for the next step, though. I think. Yeah. So here's step 2. Step 2, of course, I've been hitting at this for a while. The OH is simply going to come in. Now this says water, but basically you could actually change it so it makes it easier for you to understand. Just cross out water and say OH negative. All right, so that way it's exactly the same as it was from the previous one. All right, so the OH negative is going to come in and either attack here or attack there. All right, now here's the difference. Another difference. In that last one, what did you end up getting? Complete stereochemical inversion, because the OH had to attack from the back side. Look here, from the back side. Because you form a planar, symmetrical carbocation, that OH, he has an equal chance of attacking from either side, doesn't he? So you're going to get 2 products. One attached to one side and one attached to the other side. About 50-50, about equal amount. Okay. So let's write all this down now. The second step, of course, is going to occur very rapidly, like I said. And it results in racemization, which basically means you're going to partially convert one enantiomer into another, but not entirely. It's going to be about a 50-50 mix. See how much there is to ask about this. See how many different ways I can ask questions on just this dual mechanism. And then you got to worry about getting it confused with the electrophilic addition mechanism and the free radical halogenation mechanism. Okay? That's why this stuff gets so tough. And like I said before, this is just a cursory review of these kinds of mechanisms. When you go to college, you'll have like, every time you do a reaction, it depends on how the professor wants to teach it. He may do like all of a reaction, like as well as the mechanisms together and teach it all at once, and then put them together into the synthesis. Or he might do, like I'm doing, have like a whole chapter on just mechanisms. But either way, there'll be a lot more detail, a lot more stuff to know about it, and other ones you're going to learn too. Okay. All right. So lastly, you would expect the order of this reaction to be tertiary best, as opposed to the last one where the primary was the best. And why is that? Well, for really two reasons, if you think about it. And really, you should know there are two reasons, really. What are the two reasons this guy would go tertiary best? One, obviously, tertiary, the more carbons around the carbonium ion, the better it can stabilize it. But here's the other reason why. Okay? Those other carbons are going to cause more steric hindrance and have a harder time for the OH to get in by himself. He's going to have to form that carbonium ion first. It'd be harder for so both the steric hindrance from the last one and the fact that this guy's stabilized from this one makes it easier for him to go by tertiary. Tertiary is the best way for him to go. And that's why, given a choice, like I just did a minute ago, I'm going to give you that choice. Guaranteed. I've been doing the test. I was just drawing in not arrows, but my little dashes. I'm telling you right now, there's going to be a question about that. If you see a tertiary carbon with a good leaving group, probably going to go by I'm going to ask you which is going to go by Sn1. If you see a primary carbon, all right, given the same leaving group, probably going to go Sn2. And if I ask you questions about leaving groups, obviously you know which ones are going to want to leave better will be the less electronegative ones. The ones that want to hold on tighter, like fluorine, not going to want to leave as well.
Is there like a dividing line where you can tell whether a reaction?
Actually, no. And by the way, that's a good point. I can have guys who can do both. For example, if I have a secondary carbon, right? A secondary carbon with the right leaving group, you could expect that some of them might go by Sn1 and some might go by Sn2. I mean, that's why I will only give you the extremes. I will give you a primary or I will give you a tertiary. Secondary, it would depend on how many carbons are around it. For example, if it's just propanol and it's secondary, that's one thing. But if it's like coming off of that carbon or other carbons, it's still secondary, right? This is a secondary one. But then if I've got this guy with lots of stuff coming off of him, all right, you can understand how, even though it's secondary, he might be harder for this stuff to get in there, right? And the same also would depend on what the leaving group is, too. All right. So I'm only going to give you the extremes. I'll give you either tertiary or primary, and you'll be able to predict that, right? Okay. All right. Well, it wasn't.